All right. Welcome back, everyone. Our next speaker is Jitendra Malik. Jitendra is currently the Arthur J. Chick Professor in Computer Science Division at UC Berkeley, and he also leads the Facebook AI research in Menlo Park. Jitendra and his students have done a huge amount of highly influential work in computer vision on a variety of topics, including, as Jitendra used to call them, the 3 Rs: recognition, reconstruction, and reorganization. Jitendra has a new triangle now on vision, language, and motor control. Jitendra provided us his wisdom in the first VQA workshop 2 years ago, and now it's time to seek his wisdom again. So today, Jitendra is going to talk to us about looking for the keys. We are looking forward to hearing from you.
Thank you. Hi. Okay, so I must start the talk by explaining the title of the talk. Okay, so there's this old joke, which was that there was a drunk looking under, there's a street light, and there's somebody sort of underneath there trying to do something. So this passerby comes and asks him, "What are you doing?" He says, "I'm looking for my keys." And he said, "Where did you lose them?" He said, "I left them over there." "Then why are you looking here?" "Well, this is where the light is." So that's what is typically the case for scientists. We all look where the light is, not necessarily where we lost our keys. And one could argue that maybe that's what you should do, because if you're searching in the dark, you won't find the keys anyway. So only in the low probability that the keys happen to be where the light is, you will succeed. But I'm going to give this talk in the spirit of, let's try to think about what the real problems entail, and let's see where that goes. Okay, so this is the big picture I want to push, which is that we need to study embodied cognition. I mean, embodied cognition became like a hot topic in cognitive science sort of in the 80s, I would say, late 80s, 90s. And robotics, people like Rod Brooks pushed this and so forth. And I think we are at the point now in sort of computer vision, AI in general, where this is really how we should think about the problem, where there's an interaction between these three capabilities: vision, broadly perception; motor control, broadly planning; as well as language and semantic reasoning. So first of all, what's been responsible for recent AI successes? So the most obvious remark is big computing and big data. But in addition, it's also big annotation and big simulation. If it was not for AMT and the ability to annotate large amounts of text or images or whatever, we wouldn't be here. And this has enabled major successes of AI, and at least in the popular mind, the biggest success of AI is this AlphaGo work from DeepMind. But I would argue that this is very different from the real world of AI, which we are after. And in fact, there are special characteristics of this Go problem, right? Which is that it's a game, so you can simulate it completely. You can run a billion trials and use that. This is very different from the real world in many, many ways. I believe, and I really mean this, I think this is as irrelevant to the progress of AI as the success of Deep Blue was to the progress of AI in the 90s. So in the late 90s, we had that the world chess champion was beaten by IBM's Deep Blue program. It was an amazing success of hardware and search. And did it have any effect on the main line of progress in AI? No. Okay, I think that reinforcement learning is relevant to AI. I mean, that's not what I'm arguing against. But I am arguing that the kinds of successes in these games, they actually tell us nothing about intelligence, and they will not advance our intelligence. So AGI to AGI. So the left is AGI, but this is artificial gamer intelligence. Okay? So I sort of am expecting like a 14-year-old boy whose mother is yelling at him, but he insists on playing games all the time. Okay, so what's real intelligence about? Okay, so this is a slide which tries to capture what real biological intelligence is about. So the phylogeny of intelligence. So this slide has three main parts. The first part has to do with the beginnings of intelligence, roughly 540 million years ago in the so-called Cambrian explosion. So in a period of like 30 million years ago, 30 million years, which is just a blink of in evolutionary time, almost all the phyla emerged. And the key thing there is actually pushed by this book by Andrew Parker, that why did this explosion occur? So you had the simultaneous development of the ability to move and the ability to see. Okay, and the two capabilities play well together, because once you move, what's the advantage? You can then go and seek food in various places, but you must be able to find the food. You must be able to have some sensing of the food, and okay, that could be based on smell, but vision is very effective. Once you have creatures which have this vision and mobility together, now you have an evolutionary arms race. So the other creature whom you are going to eat, that creature may evolve camouflage, which means that you need to have a better visual system to detect in the presence of camouflage. If there is a predator and prey relationship, then the prey is going to develop shells and so forth. Predators will develop claws and so forth. So it's this sort of cycle which causes a rapid evolution. So, and of course, in modern times, Gibson has this line: we see in order to move and we move in order to see. But the point of this is that the basics of intelligence has to be sought in the sensory motor loop. And this is how everything has to begin. And for 500 million years, you could say that's the main story. Okay. When we come to, say, hominid evolution, so now we're talking about the branch going off from primates to modern humans. A key stages there's a development of the brain and the development of the hand. And in fact, the development, it's the hand, there are good arguments from the fossil record which say that as the hand developed, then there was a need for a bigger brain to enable the development of tools and so forth. And so there's like a growth of a factor of 2 or 3 in brain size, accompanying the sort of greater manipulation ability. And there was this Greek philosopher who says, it is because of his being armed with hands that man is the most intelligent animal. Okay. Then we can jump to an even later stage. So this is modern humans. So somewhere, say last 50,000 years, 100,000 years, somewhere like that. And this stage is marked by sort of symbolism. So we have language, abstract thinking, symbolic behavior, certain like art that's from these French caves from about 30,000 years and so on. And clearly language added something. But think of this as the basics of intelligence. Playing Go, I mean, when is that? That just doesn't fit into the picture. I think when we want to realistically think about intelligence, this is how we should think about it. Okay, so this is what we would call phylogeny, the evolutionary time. We can similarly talk about ontogeny, developmental time, the life of an individual child. And so this is what children do. They are constantly exploring their world. And there's a good metaphor for this. Alison Gopnik, Meltzoff, and Kuhl have this book which is called The Scientist in the Crib. And the idea is that, which is I think not a bad metaphor, that kids are just experimenting with the world. Their child reaches out with his hand, flaps at something, and then is getting signals. The signal is the proprioceptive sense, what the baby commanded, what he or she sees with their eyes, the sounds, and so forth. And with these experiments, they're building a model of themselves, they're building a model of the external world. And that's how we operate. This child, when this child, she goes to the zoo with her mother, then the mother says, oh, that's a zebra. And then the child gets it. Okay, what do our computer programs do? Oh, now the mother is ImageNet. So you say, zebra 1, this is a zebra, this is a zebra, this is a zebra, and you go on for 2,000 times. Okay? And then maybe you perform at 85% accuracy. Okay? So the difference between our programs and and this baby is that this baby is already a visual genius, because this baby has spent the previous 1 year of her life doing all this, right? So this baby knows about the physical three-dimensionality. So, for example, from that zebra, she could probably predict what the zebra would look like from a different viewpoint without having seen that zebra from a different viewpoint, because she knows about the three-dimensional world from all those experiences. So, and this is, I mean, there's another way in which one could talk about this. This is the typical way people do it in the machine learning literature or in NIPS, which would be, okay, supervised learning versus unsupervised learning. But in my mind, I really hate the term unsupervised learning, because I regard that as putting one label for a very wide slew of capabilities. Okay, it is true that the learning needs to be unsupervised. I mean, no question about that. But the term has meant in the statistical literature everything varying from clustering to PCA to whatever, right? Even in our setting, we often self-supervision is called unsupervised learning. I think that this is like saying that the world consists of dogs and non-dogs. Right? I mean, this is like unsupervised learning is like the non-dog category. This is not a category. Okay. We do need to figure out a plan of work here. And so here's where I think we can learn a lot from how child development has evolved. Okay. Children, in the last sort of 30, 40, 50 years, there have been great studies on how children acquire their knowledge of the world, acquire various skills and capabilities. And we should be looking at that literature for inspiration for how to design our synthetic journey towards a somewhat similar goal. So, there's a huge literature. What I've done is I've picked one article, mainly because it's like a good review of this. You should. So this is essentially, so I'll summarize this, which is 6 lessons, six sort of headlines, okay, for, so is that, I have 8 minutes left? Okay, no problem. Okay. The 6 lessons are: be multimodal. Okay, we saw that already. The child has sound, smell, taste, sight, etc., etc. And the beauty of this is that these cross-calibrate each other, right? Because and therefore you get a rich supervisory signal for each other. Incremental, the stages. Physical, you're actually working in the world. Explore. Be social. Use language. Okay. Now I need to note that this idea, I mean, let's try to emulate a child's journey, is really one which was proposed by Turing back in 1950. So this is the famous paper of Turing, the one where the Turing test is proposed. Everybody quotes this paper, nobody reads it. Because if you read the paper and you read all the way through section 6, this is section 6 of that paper. Usually you read the first section and it's about this imitation game, right? That's the title of that movie. But that's in the first few sections. But if you please, next time you download this paper, read it all the way to section 6. And section 6 says, instead of trying to produce a program to simulate the adult mind, why not try to produce one which simulates the child's? And then you have a program of learning. Okay, so I really believe this. So this to me is looking where the keys are. I think that our community broadly should try to emulate this child development agenda, go through the various stages of that. And I think it is not a hopeless task. I think some stages of it we are already able to do. And we will use all our hammers. We'll use neural networks and stochastic gradient descent and all the various tools we have. Those are all mathematical techniques. You need to know what problems to pose. And I think the child development agenda poses the right set of problems. Now I'll go through a very whirlwind tour of some work from which makes this more concrete. So this is work from our lab, which is on sort of let's see if I can get this to move. So, okay, so these are experiments where basically the robot is playing the role of the child, and without any external supervision, the robot pokes objects and takes pictures before and after, and uses this to build a model of what every action is. Now you can throw the usual neural network mumbo jumbo, right? So there is a input image, output image, and an action, and you're trying to find the relationship between these. So you want to acquire a forward model and an inverse model. Okay, and you can do that, and then once you've acquired this model, it generalizes in certain ways. You can do planning. Then here's another example of this sort of technique. This was for a rather different kind of task, learning how to manipulate a rope to get a pattern such as tie a knot and so forth. And same paradigm basically applies. More recently, we've been doing things like take the segmentation problem. So in the segmentation problem, we classically would have humans mark the boundaries of every object and then train your mask RCNN. But this is ridiculous. When a child is learning the notion of an object, how can you provide that supervisory signal? You can imagine a supervisory signal of this is a zebra from a mother, but you're not getting a supervisory signal of these are the pixels in the image which correspond to a zebra. How do you ever even supply that? Okay, so what you can do is if you have a model, you pick up objects, and if you can pick it up, it's an object. If you can't, it's some background. And with this idea, we have been able to essentially acquire a segmentation system. It does not perform as well as the one with supervision, but the interesting point of this is, I think, the right way. This is along this agenda. Okay, and I'm going to skip quickly. Okay, now let me come to be social and use language. Okay. So let's talk about social. Computers today have very low social intelligence, okay, whereas this is a very important capability for children. So some of you have seen this slide from me before, which is that in this slide, there is obviously labeling the objects and recovering 3D, but to me the interesting question is whether this man will put some money in the musician's basket. And that's really about social interactions, not all this sort of geometry and classification. Okay, now why is this hard? It's hard because this is about understanding human behavior, which means that it is not just about patterns of movement, but it's really about goals and intentions and so forth. And here's a slogan that I like to use. It's really action is movement plus goal. And what we are doing when we are winning on UCF 101 or HMDB is really patterns of movement, not trying to understand the goals. And I'm going to run this. This is a very cool video. Some of you may have seen. So this is from Tomasello's lab.
Oh.
Okay, and there are actually many studies of this type which show that children can infer goals and intentions. Okay, and they do not need 1,000 examples for this, right? So you essentially have to have these agents who have basic social intelligence. Okay, so I'm going to. So let's take another example. So now I'm getting closer to language. Common sense knowledge. Such as, for example, interpreting some text about a restaurant meal. This is a classic AI example from going back to like 70s and 80s, from Shank and people like that. And we would not use that way of hand building and knowledge now. We would learn it from common sense knowledge. But at the end of the day, we do need models of physical behavior, objects falling, liquids pouring, but also of social behavior. And that is the only way we can make sense of the world. So there is a classic exposition of why we need models. This is from Craig, 1943, which says that if you have a model, you can do forward simulations, and this is how we can reason and plan. This is very important, and amazingly, this given current excitement about model-free reinforcement learning somehow forgets this basic idea, which really goes back to the 40s. And I think this is, again, a bubble which is going to burst. Again, reinforcement learning is a good thing in general, but model-based reinforcement learning makes a lot more sense than model-free reinforcement learning. But okay. So I talked about social, then about language. Now, why do we care about language? So I think that this is actually an interesting question. Why did language develop at all? Because I mean, there are colleagues of mine with whom I shall not name, with whom we have had these discussions, who argue that language is completely unimportant and we should really focus on what primates, apes can do. And vision is there. I mean, and those have as good vision systems. And I disagree, because we actually have evidence that once the language capabilities develop, then things go much faster. And this slide shows, all the, so it could be that for coordination of people, here are long lists of what applications language could have, okay? And, okay, so I'll comment on language research today, the last two slides, okay? So we've had great success on problems such as machine translation, but the techniques feel to me like Searle's Chinese room. It's like there's some sequence of symbols in French which are being, and then you're outputting sequence of symbols in English. So it's a sequence to sequence kind of model, but with no understanding built in. If you want a detailed attack on that, there's an article by Doug Hofstadter in The Atlantic, which I think is not every bit of his writings are to be taken seriously, but this article is quite good. I believe in grounding, so I like work such as VQA, but much more is needed. So we know certain things. We know that interaction and shared attention is essential. So there are studies of sort of parent, child, and an object. So there is triadic attention. So the parent is not teaching the child grammar. The parent is interacting with the world, and the child is interacting with the parent and with the world. So there is this common attention thing. There's this great example of a hearing child of deaf parents they decided not to teach him sign language, but just expose him to lots of TV. And the child did not develop good language. Because so whereas what are we doing in our natural language systems? We are trying to work from huge amounts of text. I think that at a later stage, that is very appropriate. That's how we also learn. Later in life, we learn about concepts which we have never encountered directly. So language from text is perfectly okay. But the early stage, we are sort of skipping. And so this is an argument for data sets not being enough, and you need environments. But this is a talk in the paper. I'll skip that. Here's just one study which tells you about how language actually, it creates categories which, so children, once they know that two words exist, this enables them to categorize them better. So in fact, language helps with vision in a certain way. I'll conclude here. Thank you.
Thanks a lot, Jitendra, for the amazing talk. We have time for questions.
Thank you for the talk. So when we look at children for inspiration, so it feels like they do come with a lot of the genetic makeup, right, over the years, the evolution and all that. So what parallels would that be for our techniques? Because we always start with some sort of random initialization per se. And
so the neural network architecture, so if you want the crude version, the neural net architecture that you build in before you start training it, that's the result of evolution. And then the rest is exposure to experience, which is what your data should give you.
The idea of learning language like a child is a really great idea, but I guess there's billions of parents around the world that invest thousands of hours to provide that learning environment. How do we provide that environment for machine learning agents?
Fair question, and I think people are trying to do this, but this is where I think what worked in vision will not work in language. So in vision, what worked was static data sets got us a long way, whereas here interaction is necessary, right? So therefore, even in vision, we are moving to sort of environments where you can study active perception. Here, I think we will have to create some kind of game situations from which we can get people to people's interactions in those game situations will generate the right kind of training data. So that's a broad stroke thing. I don't know the detailed answer, but I think people are working on this. As I said, I don't really work on this, but I believe that something like this is necessary. Whereas if you look at the history of language, it's all been based on text, right? Going back to the Wall Street Journal corpus, or there's various bilingual corpus, right? And I think that this can't go on.
Questions?
Thank you for your talk. So what is the biggest missing piece in between natural language processing, like the text data, and the visual data or AGI or whatever project that you're working on? What is the...
No, I think it is, we need language data acquired in the context of interactions.
I see.
So we need examples of, so if we could record children with their mothers and fathers, right? So that, but people have tried to do that, but they need to record everything, which you don't do. You record some segment of it, and it's way too intrusive and so forth. But I can imagine that you could, if you could collect like the entire sensory motor experience of the child, that might be that. And you acquire 100 such examples. I mean, this is one way. I think we will have to find some other alternative because this is too painful and too difficult to acquire. I think if we could have a set of games in which people would play because they are fun, but we would, as a result, acquire data, which I think that we always need some proxy for the real experience. We don't actually do exactly the same way. AI is not built on exactly replicating natural cognition. We have to find some proxy.
I see. One follow-up question. So I'm from natural language processing background. So we only train our model on text-based data and optimize it like for pantry bank and only text data. So what kind of bridge that the NLP community need to contribute to this vision-related or robotic or like...
Yeah, so you should, I think those data sets are like, we have our own versions of this. It used to be MNIST and ImageNet, and that's an addiction and you need to get out of it.
Okay, I see a couple of hands, but I think we are running out of time. We do have a panel session at the end, so please feel free to ask as many questions as you can in the panel. Thanks a lot, Jitendra.
Thank you.